So this chapter has two main focuses or two main sections. They could have split it into two separate chapters, but they combine them. Basically, the first is just ideal gas mixtures, nothing to do specifically with air and moisture or water vapor in air. But the last half, or the second half, is what they call psychrometric applications. There where we deal with specifically focusing on ideal gas mixture known as the air that we breathe. It behaves as an ideal gas. It's well characterized as an ideal gas. It's made up of nitrogen primarily, oxygen, hopefully a lot, CO2, argon, and some other trace elements, as well as water vapor, H2O. And so we'll be dealing with moist air, study of moist air. So we'll start off with just a backup, kind of review what was covered in maybe your chemistry class with ideal gas mixtures. So we review what is a mole fraction. So when we have a gas mixture, it can be made up of multiple components. And so this textbook talks about the mole fraction and uses the symbol Y for it. And it'll have a subscript I. So that's the mole fraction of component I in the gas mixture. Okay. It would be equal to the number of moles of that component, let's say it's argon or CO2, in the mixture, and the mixture would have a total number of moles. I won't add the subscript mix here, but I'm very tempted to. But when you see N without a subscript, it's the total number of moles of the mixture. Okay? And when we say moles, I'm using mole or kilomole. And often we work in kilomoles, but if I say mole, you could work all in moles or you could work in kilomoles. Same thing. Just a factor of 1,000 scaling. We also have volumes and volume fraction. So we're going to talk about a description, and we'll talk about the volume fraction is equal to the mole fraction. That's on the next slide. The next one is mass fraction. Now, some books will go and they'll use X. They'll say, well, I used Y for mole fraction. Let me use X for mass fraction. Very confusing to students. So this author of this textbook said, I don't want to introduce a confusing notation that you try to remember. What was Y? What was X? X is quality, right? So they said, let's use MF, mass fraction. That's a little deviation from a lot of things. Usually we just have one letter like P or T or X or Y for an entity. This is two of them. F is not subscripted. It's just MF for mass fraction. And you can have a component I, and so there'll be a mass fraction in that ideal gas mixture of the species I. How it would be defined? Well, it would be the mass of that species divided by the total mass of the mixture. Look reasonable? So that would be your mass fraction. You can jump back and forth between a molar analysis and a gravimetric analysis. What do you mean by gravimetric? Well, this is another way of saying an analysis by mass or of the mass. Gravimetric, like, did you recall when you first learned what big M was? Big M was the molar mass, but a lot of people used to call it, or still call it, molecular weight. How many people learned it as molecular weight? See? So a lot of people. It's that gravimetric. So it took a while before people figured out there's a difference between the weight of an object and the mass of an object. Okay? So you'll see that weight of something referring to its mass. So the molecular weight or the molar mass. Okay. So if I have the molar mass, what are the units on the molar mass of, let's say, a species I? Do you recall the SI units? Okay, let me first clicker question. How's that for the day, huh? So let's see if I can do this. Okay, is the units for big M, the molar mass, is it kilograms per kilomole or kilomoles per kilogram? Answer A or answer B? Which is it? SI units for big M, the molar mass. Kilograms per kilomole or kilomoles per kilogram? Let's go ahead and stop it. And very good. So it's kilograms per kilomole. Why wasn't it kilomoles per kilogram? They could have done it, but it started that way and it stayed that way. And I'm thankful that when I open one textbook and they talk about the molecular weight or whatever, molar mass, they didn't invert it. And every now and then you'll see that in science and engineering. Oh, the Lewis number in this textbook means this. If you open a different textbook, the Lewis number is the inverse of what the previous textbook had it as. Sort of haven't settled down in the science and engineering in some areas. Okay, so there it is. So if I want to know the mass of a species and I know the amount of that, then I multiply by the molar mass. True? And then I can go back and forth. The amount is equal to the mass divided by the molar mass. True? Yeah. So we have the molar description and the mass description of our components. If I said that y sub I is the mole fraction, isn't it? If I sum up over all the components I, what does that sum equal to? 1. How about the mass fraction? If I sum up the mass fractions over all the components, is that equal to 1? It is as well. Okay. Now we'll talk about partial pressures. To discuss partial pressures, often we introduce the concept of the Dalton's model. So here's a description of Dalton's model. A mixture of several ideal gases. Think of just two components. Component 1 and component 2. Color-coded red and color-coded blue for illustration purposes. They have the total pressure equal to the sum of the pressures exerted by each of the constituents as if they were alone at the same temperature and volume as the mixture. So here's the mixture. And I tried to draw the box the same shape. So the volumes are the same. So V1 is equal to V2 is equal to what the original volume was. The temperature, likewise, the temperature of the gas in the first container, which is only component 1, is equal to the temperature of the gas in the second container, which is only component 2, is equal to the temperature of the original gas mixture before we conceptually split them out. How about the pressure? Well, Dalton's model says that the pressure in 1 and the pressure in 2 summed up equal the total pressure. So the sum of the pressures exerted by each of the constituents as if they were by themselves. So if I said, what is equation for a piece of 1? It's always an ideal gas. I can use the ideal gas equation. Would it be equal to the number of moles of component 1, R bar T divided by V? Likewise, I could go back to this original gas mixture and I could say, isn't P equal to the number of moles total R bar T divided by V? And then we'll just take and divide this equation by P on the left-hand side and by P on the right-hand side, but let's put our NR bar T divided by V and then start canceling some terms. The V's cancel, the R bars T's cancel, and so what we find is that the pressure 1 divided by the total pressure is equal to the amount 1 divided by the total amount. Isn't that the mole fraction? And I put an I there. That's generalizing it, but I'm deriving it for 1. You can do the same thing. and you find that P2 divided by P is equal to Y2. If you only have two components, is it true that Y1 plus Y2 is equal to 100%? Sure. And you could generalize it to many more components, but what you find is that you could replace Y1 by P1 over P, Y2 by P2 over P, and so you get P1 plus P2 is equal to P. The sum of the two pressures, what we call the partial pressures, is equal to the total gas pressure. How do you calculate the partial pressure? Well, you assume that it's as if it were alone at the same temperature and volume as the original mixture. How do we use this a lot? We use it a lot if I unravel this equation right here and I say that the partial pressure of component I is equal to the total gas mixture pressure multiplying by the mole fraction. That's how we use that a lot. There's a number of problems that I have solved, and so instead of solving them again, I encourage you to watch some of the stuff I've recorded and put out there on YouTube, because I don't think they're all that challenging until we get later in this chapter, chapter 12. Amagat's model, or partial volume concept. We have the partial pressure concept. You also have the partial volume concept. Here, you can read the definition, but it's as if they were alone at the same temperature and same pressure, but in different volumes. So you can see that this volume of this box is smaller, and this volume of this box is smaller. And if you sum those two volumes, you have the total volume. Try to draw that to scale for you. And so when we talk about the volume, we talk about the total volume is the sum of volume 1 plus volume 2, thinking about this is for component 1, this is for component 2. Okay? What about the temperature? They're the same. What about the pressure? They're the same. So when you say, what about this volume of 1? Could I calculate using the ideal gas equation? What would that ideal gas equation give me? Would it be that this is the amount of 1 R bar T divided by P? Could I do the same thing for the total gas mixture? So V is equal to total N R bar T divided by P. I do the same thing. I bring that equation over, divide by V on the left, divide by N R bar T over P on the right, and cancel the P R bar T's. And we have the same idea that V1 divided by V is equal to N1 over N is equal to Y1. So what we would say is we would say the partial volume of that ideal gas mixture divided by the total volume of ideal gas mixture is equal to the mole fraction. Or rewrite it just like we did with the partial pressures. V sub I is equal to V times Y sub I. Okay? Likewise, you can find that the sum of the partial volumes is equal to total volume. Well, that's where we started with, didn't we? Yeah. And so it's less common to talk about partial volumes, but it is common to talk about it. Because back here, when we start this chapter, we're going to talk about how you describe ideal gas mixtures. Well, sometimes they talk about the mole fraction. Sometimes they talk about a volume fraction. What's the difference? Well, the mole fraction is Y sub I, defined like this one. What about the mole fraction? Well, it would be V sub I divided by V. Is that equal to Y sub I? It is. And we just demonstrated that using Amagat's model and the partial volume concept. This all applies to ideal gas mixtures. As soon as you start deviating from ideal gas mixtures, they don't behave as ideal gases. You can't apply the simple ideal gas equation. Things change, and that's not true in general. But for an ideal gas mixture, it's true. So you'll see these terms. Oh, the volume fraction, it's 20% this and 80% this. Okay. They just told me the mole fraction. And they'll say, oh, the gravimetric analysis, it's 30% this and 70% that. They just told me the mass fraction. Okay? A lot of times we have to calculate changes in a property like an internal energy for an ideal gas mixture. Well, you would think, if I knew the amount of the ideal gas mixture, the total amount, and I knew the change in the specific mixture internal energy, then I could make that calculation. Does that equation look reasonable? You could also say, well, if I knew the total mass and I multiplied by U2 minus U1, those don't have a bar on it, and they're lowercase, so it's specific. Notice the units on this one. This would be like in kilojoules. This would be kilojoules per kilomole. This would be kilojoules per kilogram. True? Okay. Let's say you had more than one component, because it's a mixture. Would I generalize this by saying, oh, it's the sum over all the components of the amount of each component times U2 bar minus U1 bar for each component. Sum over all the components I. Does that look reasonable? It's additive. Yes, you would do the same thing. If I had a mixture where I had just a solid put into a liquid bath, and I'm doing some change in internal energy calculation, same calculus. You would do the same thing. You would have the sum of the mass of that component, U2 minus U1 for that component, over all the I's. Make sense? Okay. This does pertain to an ideal gas. What do we recall? There's three things whenever you see an ideal gas. It's PV is equal to nRT. True? What other thing do you recall when you say, oh, it's an ideal gas? U is a function of temperature only, and H is a function of temperature only. Okay? Now, if I said, what is the specific heat constant volume for any fluid, any substance, solid, liquid, gas, ideal gas, it's defined as the rate of change of internal energy with respect to temperature holding volume constant or specific volume constant. Do you like that definition? Now, in special cases, this simplifies to be equal to not the partial derivative, but the ordinary derivative of U with respect to temperature. When does that happen? It happens when U is a function of temperature only. It's not a function of temperature and specific volume or temperature and pressure. It's just U. So a lot of times for ideal gases, we do like to use constant or specific heats, and often we use constant specific heats. So if I say, if I wanted to make this calculation up here with that information, I'd say, okay, well, sum over the amounts times the specific heat constant volume of each of those components times the temperature change of the component. Make sense? So this is, you do the sum over all the I's. Make sense? Oh, there's a C sub V bar I need right there because I'm doing it on a molar basis. Let's do it for the mass basis. It's also equal to the sum of the amounts in mass times C sub V for that component times T2 minus T1. This is all for that component, over all the I's in that mixture. Do Do you see how you would do the same thing for changes in an enthalpy? Instead of C sub E, it's C sub P. Instead of U's, it's H's. So we covered the specific heats for the ideal gases and see how they're used. What about changes in entropy for an ideal gas? Well, you remember something like this. You would say, let's work on a mass. Well, let's stay with it. We'll put molar on one side and mass on the other. So S2 minus S1 would be the amount times S2 bar minus S1 bar. Or it would be the amount in mass times S2 minus S1. That's written as if it's not a mixture, but if it is a mixture, then we'd say, well, let's sum over all those components of S bar 2 minus S bar 1 for that component. Sum over all the components. Likewise, S2 minus S1 over all the components. Make sense? But here's where a lot of students, they love that ideal gas. They say PV is equal to nRT. They learn that. They want to apply that to steam in the two-phase region. You're past that. You don't make that mistake, right? You wouldn't apply PV is equal to nRT for subcooled liquid, would you? No, it's only an ideal gas. And then they finally figured out, oh, U is a function of T only. Great. H is a function of T only. Great. Let's continue the pattern. S for an ideal gas is a function of T only. True or false? Oh, it's false. This is false. You learn that. So what you need to think about, well, it's a function of two independent intensive properties. Often we like to work with temperature, but another popular one is pressure. Or you can write it S as a function of temperature and volume. Okay? So, armed with that, I have to think about this. It's probably I'm going to talk about the partial pressure because I don't have the partial temperature concept. There's no partial temperature, but I do have partial pressures when I have ideal gas mixtures, as well as partial volumes when I have ideal gas mixtures. So the first time you see this, it's like, ooh, a little crazy, but it's workable, doable. So here we go. It's equal to the sum of the amounts summed over all the amounts times. How would I rewrite this equation using constant specific heats? I would say C sub P natural log of T2 over T1 minus R bar natural log of P2 over P1. Everything in there pertains to component I. So when I see this specific heat, I need it for that component I. When I have temperature at 1, it's for that component I. Okay, it's not a partial temperature, it's just the initial temperature of the mixture where I was in it at state 1, likewise at state 2. But here we have the partial pressure. So what can happen is you can change the pressure of the mixture. Okay, and hence the partial pressures would change. It's a little easier in this chapter because we have non-reacting systems, non-reacting ideal gas mixtures. Guess what happens in the next chapter? We have reacting gas mixtures. So when you have non-reacting gas mixtures, what I know is I can replace the partial pressure by the total pressure times the mole fraction. True? And the total pressure times the mole fraction. If I have non-reacting mixtures, the mole fractions don't change and they cancel. And so a lot of students leave this chapter where we're dealing with ideal gas, non-reacting mixtures, and they say, this is easy. Whenever I see this P and P, I just replace it by P2 over P1 because the Y's cancel. Good, remember that? But in the next chapter, the partial pressures change because just let you know, maybe something like this. Maybe I bring in methane, CH4. Maybe I bring in oxygen coming in. Maybe I come out with CO2 and H2O. Maybe I have a little bit of unburned CO2 and maybe a little uncombusted CH4. I've got to worry about entropy changes in this system. I need to know the actual partial pressures of each component on each inlet and outlet stream. Okay? But let's not get too complex. For right now, they are non-reacting, and hence it simplifies, and there you go. If you do it on this is a bar right here, sorry. Why is that a bar? Yeah. What are the units on C sub P bar? Kilojoules per kilomole Kelvin? True. What are the units on R bar? Kilojoules per kilomole Kelvin? True. Same units. Okay. You could rewrite it on a mass basis. The sum over all the mass of each component times C sub P, natural log T2 over T1, minus R, natural log P2 over P1, each for those components I. Okay. What are the units of C sub P? Kilojoules per kilogram Kelvin. What are the units of R? Kilojoules per kilogram Kelvin. How did I go back? Just remind me. How did I go between R and R bar? Using cap M, using the molar mass. True? So if I have R bar, do I multiply or divide by cap M to get R? Like this? Look good? Okay. Now, armed with that, how do I go between C sub P bar and C sub P? What is the relationship? Is C sub P bar, is it 1 over the molar mass is equal to C sub P? Has to be. Look good, right? Yeah. Units look good. Concept look good. Now make sure, because we're talking about a component and a component and a component right here. But over here, we just had a component and a component. R bar was the universal gas constant. True? Okay. Okay. What I want to do is I want to talk about this problem. In the time we have left, it takes us a while to set up and solve these problems. They're a little tedious because I think it's good, especially early on, solve it using mass description, solve it using molar description. But I don't have time to solve it both ways, so I'll just pick one and go with it. So what we have is nitrogen. Let's call right here N2. It's at 40 degrees C coming in. So 40 degrees C, we convert that to Kelvin, 313 Kelvin. And it's 200 kilopascal coming in. And the volumetric flow rate, 60 meters cubed per minute. It enters a well-insulated mixing chamber. Well, 2 pipes that are well-insulated, and they join, and it's well-mixed when it comes out. And mixes with argon. Here's the other stream. Entering at 110 degrees C, which is 383 Kelvin. Pressure 200 kilopascal. And 20 meters cubed per minute. True? It's going to mix, and it's going to go out. Okay? So right over here, we're going to have a mixture coming out. It'll have some mole fraction of nitrogen. It'll have some mole fraction of argon. True? It'll have one temperature representing the mixture temperature. It'll have one pressure representing the mixture pressure, and they told us it's 200 kilopascal in the problem. So there's no pressure drop. Both inlets are 200 kPa, the outlet's 200 kPa. All right. Determine the mixture temperature going out. What's the exit temperature? This is exit temperature T2. We'll call this 2, here's state. Well, should I call it 2 or 3? Maybe I should call this 1 on the inlet, 2 on the inlet, and 3 on the outlet. So I'll change the numbering system I'm looking for T3. All right. Let's solve for T3 and then start in on part B. All right. Looking at it, can you estimate what T3 is going to be? Is it going to be less than 40? Is it going to be greater than 110 degrees C, or somewhere between 40 C and 110 degrees C? Somewhere in between. True? Somewhere in between. So if you get a number that's not between the inlet T1 and the inlet T2, between those, you have an error. Just look for your error. True? So what am I going to do? I'm going to employ a control volume, and I'm going to do a first law energy balance. True? And then, do I have any work? Do I have any heat? No, well insulated. Neglect changes in kinetic energy and potential energy. I can play with the equations, a few steps in manipulating, but you should be getting good at something like this where you have, let me try and write it over here, that I'm going to have the molar flow rate of the nitrogen times the specific heat constant pressure on a molar basis of the nitrogen times it goes out hot, comes in cold. T3 is greater than T1. Isn't 3 is going to be greater than 40 degrees C, but less than 110 degrees C, the argon. And that's equal to the molar flow rate of argon, C sub P bar of the argon, T2 minus T3. It's kind of like what the nitrogen was heated up and the argon's cooled down, so they come out at the same temperature. Are you getting good at the first law? Is that too much to write one? Because I want to conserve board space, and I think you've been able to solve first law analysis, open systems. So we get an equation for T3. It'll be something like the molar flow rate of the nitrogen, the specific heat of the nitrogen, the inlet temperature of the nitrogen, the molar flow rate of the argon, the specific heat of the argon, the inlet temperature of the argon, divided by N dot nitrogen, C sub P bar nitrogen, plus N dot argon, C sub P argon. Algebra look okay? Do I need to pause? Are you with me? Do I have an error? Sometimes I do. How do I find the molar flow rate of the nitrogen? Well, they gave me this information, this molar flow rate. Is that AV, the symbol AV for molar flow rate? Is that the symbol that the book uses, the symbol that you would use to be consistent with the textbook? It's the product of the area and velocity, kind of one-dimensional normal velocity through the pipe. And this would be the AV of the nitrogen. This is the volumetric flow rate of the argon. So the molar flow rate is proportional to the volumetric flow rate of the nitrogen, true? But it's not just equal to it. So what I have to deal with converting from, I have to use what property? Specific volume. That's exactly right. So do I multiply by V bar or divide by V bar to get this equation to work out? Divide by? All right. And this is the specific volume. That's a bar over it on a per unit mount or per mole for the nitrogen. How do I get V bar of the nitrogen? Ideal gas equation. Ideal gas equation, true? So what is that equation equal to? The R bar T of the nitrogen coming in. This is the nitrogen all coming in state 1, state 1, state 1. So it's state 1 divided by pressure, nitrogen coming in, state 1. True? Is this an R bar and a V bar? Both of those have bars on them? Look good? Do I need a molar mass in this equation? Or no? It looks good? And we check the units. What are the units on this V bar right here? Is it meters cubed per kilomole? That's the SI units. All right. So I know it's a few steps, but it's like bing, 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 bing. I've got the end dot. I can do the same thing for the molar flow rate of the argon. True or false? True. Now we have to struggle with the C sub P bar for the nitrogen and the C sub P bar for the argon. A lot of times in the textbook or this problem, they'll just give it to us, but they didn't give it to us. So how do I get C sub P bar for nitrogen? I can probably find C sub P without a bar on it for the nitrogen from a table in the textbook. And I'll think about it and I'll say, well, I don't know what temperature to evaluate. I know they list specific heats for nitrogen, it's function of temperature. Well, you guess. You say it's going to be between 313 and 383. You want to guess a number? They go in 50 degree Kelvin increments. Is it 250, 300, 350, 400, 450, 500? Which one are you going to pick? 350, and don't bother slowing down on the interpolation. Okay? All right. So get that value evaluated at like 350 Kelvin out of the table. Okay, now, next thing is, I need probably another parameter in this equation because C sub P bar is not equal to C sub P, but what's the relationship? What parameter do I need? Molar mass. Okay. So this, do I multiply by molar mass of nitrogen or divide by molar mass of nitrogen? Use your units to help guide you through that. It's multiply, isn't it? What are the units on molar mass? Kilogram per kilomole. Good. Now the other one is a little different. So this one came out of the table, but I can't find C sub P of argon at 350 K in a table anywhere in this textbook. What am I going to do? What am I going to do about argon? Yeah, I'm looking for one key word.
There was something about the monoatomic gas.
It's a monoatomic gas. And this textbook makes it harder to get properties for monoatomic gases than it should. So guess what? It's really easy to get C sub P bar for the argon right away because it's monoatomic. And then, so what you do is you take a look in the textbook. I think it's table A21. Table A21. So this information for the nitrogen came out of table A20. C sub P bar for the argon comes out of table A21 in this textbook. All right, so what do we get out of table A21 where argon's a monoatomic gas? Well, what they give us is that the bottom row is for monoatomic gases, and they say alpha is 2.5. Alpha is C sub P bar over R bar, so it's 2.5 times R bar. That's C sub P bar for argon. Guess what? C sub P bar is for helium. 2.5 times R bar. The molar specific heat for any monoatomic gas is 2.5 times R bar. How many monoatomic gases are there? Well, they list them. They say helium, neon, and argon are the three that would be kicked around in this textbook. Make sense? If you wanted to get specific heat on a mass basis for argon, yes, you would use the molar mass now and convert it. But we're going to do it only in molar basis. So there you go. So when I compute this, I find that T3 is coming in right at 324.4 Kelvin or 51.4 degrees C. I encourage you to step through the math on that. I'm leaving out details, but I'm giving you the roadmap. True? Watch out for units. What is this unit right here? Minutes. And the temperature calculation, it doesn't matter. For the next calculation, it does matter. Okay. What about for part B? What is this next calculation? What do we want to solve for? The rate of entropy production. Well, I don't think there's any entropy production. All you're doing is mixing. Is there going to be any entropy production? Why? Temperature's not constant? Is that the driver? Or is there something else going on? Think about this. Is it reversible? Somebody says, I've got a stream of mixed argon and nitrogen. Turn it around, and I want you to develop a nice simple system to take the argon-nitrogen mix and give me a pure stream of nitrogen and a pure stream of argon. Hey, make it easy. Just leave it all the same temperature. Really what drives the entropy production is the mixing process. Then second, there's an added component because one is hot, one is cold. That even adds to the entropy, the irreversibilities. Okay? So how am I going to solve for, well, first of all, what am I asked to solve for? What symbol do I use for this answer for part B? Sigma dot. Just like I didn't play too much. What were the units for T3? Maybe Kelvin or degree C. What are the units of sigma dot? Kilowatt? Kilowatt per Kelvin. Kilowatt per Kelvin. Okay. So this has units of kilowatt per Kelvin. Now, how do I do this? Well, I have just maybe enough room right here to tuck it in. What am I going to do? For this control volume, I'll apply second law, doing entropy balance. Entropy balance. So, sigma dot is equal to, now I know there's a number of steps here. You would apply the general form and you say, hey, there's no entropy transfer with heat transfer across the boundary of this control volume, so that term is zero. It's steady state, no accumulation, no depletion. And you would come up with something like this. You'd say the molar flow rate times the change in the molar entropy from coming in at 1, going out at 3. All of that for the nitrogen times the molar flow rate going out at 3, in at 2, all for the argon. Does that equation look good? Sigma dot's equal to that. Look good? Is it readable? It's kind of like the argon and the nitrogen have a higher entropy, S3, going out. Hence, that's what was the generation. That's sigma dot. Okay. So the molar flow rate, I think we've got that under control. We did that for part A, did we not? What about this S3 minus S1? Is that equal to C sub P natural log T3 over T1 minus R bar times natural log of P3 over P1? Does that look good for the change in S? Now, everything in here is for the component nitrogen. Just like we'll have the molar flow rate of the argon, C sub P bar natural log T3 over T2 minus R bar natural log P3 over P2, everything in there for the argon. Okay. I'm running out of board space, but what I'd like to do is I'd like to just describe that the P3 divided by P1, okay, when I look at, here, maybe I need to do it up here. When I look at P3 and I divide by P1, and this is all for the nitrogen and the nitrogen, right? What was P3 of the nitrogen coming out? Is it going to be the mole fraction of the nitrogen times P3? Is that the partial pressure of the nitrogen coming out, the mole fraction of the nitrogen times P3? And then what about coming in stream 1? Is it equal to 100% because it was pure nitrogen coming in stream 1 times the pressure at 1? Yes? And do these two pressures cancel because they're the same magnitude? So here we have a case where the natural log, or the ratio of partial pressures, turns into the natural log of the exiting mole fraction. This right here is the exiting mole fraction of the nitrogen. Likewise, this is the exiting mole fraction of the argon. All right. What about R bars? Those are easy, 8.314. What about the C sub P bars? You did that before for both of them. And the only thing is you want to watch your units, because just watch it for 60 seconds is 1 minute. Because the molar flow rates, the volumetric flow rates are coming in cubic meters per minute. So this turns out to be 0.234 kilowatts per Kelvin for the nitrogen by itself, and 0.196 kilowatts per Kelvin for the argon by itself. And when you sum them up, the rate of entropy production total is 0.430 kilowatts per Kelvin. A lot of entropy generation due to the mixing. Some also due to the temperature. I didn't try to separate them, but there's the answer for part B. Any comments or questions? Thank you for your attention.